Oh yeah, chapter 4 review. Here we go.
Here it is. We're coming.
We got Miss Boyer here. Now this is her
We
first
do.
time at the camera.
Yeah, so.
Hello.
Hello.
How are you?
I'm doing fine.
Oh, you know what? You know what? Wait a second. Hold on a second.
Okay.
Uh-oh. Do I have any extra insulators? Oh my gosh. Oh my gosh. Let me
Yes,
give
you
it some
do.
props out for the insulator drive.
All right.
Let me put this dirty thing on here. Here,
Yeah, Aldi.
insulator.
Here we go.
Bring in used insulators for the insulator drive, everybody. Let's help out.
Yeah.
We already hit our goal of canned goods. Here's another insulator. Here we go. Look at this. I'm just insulating myself like crazy. Stuff with high specific heat.
Right.
Look at this. Look at
Okay.
this. Hold on. I'm even have a hat
Oh,
too.
man. Oh, wow.
I'm just insulating myself like crazy. Hold on.
Please excuse the interruption.
No.
Thomas Riley.
Here we go.
Please
Here we
report
go.
from 300.
More
Thomas
insulation,
Riley
more
from
insulation.
300.
Here we go.
Oh, wow.
Look at me. Used coats, used sweatshirts,
Yeah, the
Bring 'em
snow
in.
outside.
snow outside.
Right.
Bring them in.
You're
Here we go. Another one.
warm today. Warm today.
And finally, let's go turn back the clock.
Oh.
Let's go back to the old Science Olympiad team.
Man.
Here, I'm gonna look like the Stay Puft Marshmallow Man. Here we go. Insulator. Oh, the good old Science Olympiad team.
Okay.
Yeah!
Yeah.
Bring
All
in those
right.
coats, use sweatshirts, jackets, help out the Friends and Community Club, and everything else.
All right.
Some insulators right here, right?
Got it.
Overpriced junk, cheaper, high quality, better insulator. Okay, let's talk
Okay.
about this stuff. We're in chapter 4, and we talk about the flow of heat being energy. Heat can enter something, and it can leave something. Well, how do we know? First thing you have to know is heat always goes from warm to cool. Warm to cool, every time. So think to yourself, when we ask you, which way is heat going to flow? Take a step back for a second and think. Where is it warmer? Where is it cooler? So then you'll look, okay, it's warm in this area, so the heat's going to go from the warm place to the cool place. Okay? And we'll look up here. Take a look up here. Here's a couple examples. Here is water. Isn't that beautiful? And here's ice cubes. Okay? We're good with
Yeah,
the camera.
got it. We got
So
it.
right here we got really cold ice cubes.
We do.
So you've got ice cubes and you got water, H2O. Which one's warmer? The water or the ice cubes? Well, the water's warmer.
Sure.
So which way is the heat going to flow?
It's going to go from the water to those ice cubes.
You got it. So what'll happen is the heat goes, sees these cold ice cubes, goes, yeah! And it goes like this. And attacks the ice cubes from warm to cool. There's your heat. Heat, heat, heat. And what eventually happens is the ice cubes speed up. Their kinetic energy, their molecules speeds up. They have more thermal energy and the temperature rises. Well, how do you know? It starts to melt. And then eventually it cools down the drink. Okay?
Right.
Next example. Room temperature water. We'll say it's about 75 degrees. Freezers below freezing, 31 degrees. So we're comparing the water, warm water, and air. But it's air in the freezer. So which one's warm, which one's cool? The water's warm, the freezer's cool. Which way is the heat gonna go? From the cool freezer to the water?
No way.
It'll leave. Watch this. Warm to cool. Now the freezer is a motor, an internal environment that maintains that cold temperature. Eventually this temperature drops, and that's how we get ice. Because the liquid's molecules slow down because the heat's leaving the water. The molecules slow down, eventually become a solid. But even though they're a solid, the molecules are still moving. Okay?
Got it.
And let's just give one more example real quick. Let's go, let's do this. Let's say I've got a pizza. And the pizza's really hot. I just took it out of the oven. Pizza's really hot, but I'm hungry.
Right.
I want to eat it now. So I put it in the freezer. Again, you ask yourself on the video, think about it. Which way is the heat going to flow? From the hot pizza to the cold freezer, or from the cold pizza to the hot freezer? I'll give you a second. It will flow from the hot pizza to the cold
Please excuse
freezer.
the interruption. Mr. Greco, please return to your room. Mr.
Coach
Greco,
Greco,
return to your room. Thank
This
you.
is the second time you've been calling our videos. Maybe you need to be in the next video. Hot to cool. Okay, so the pizza
Right.
cools down. Okay, really important. You need to know that stuff. One more example. Let's do one more example. One more example. How about what I just thought of one and I forgot it. How about what do you think of something that wants to heat up?
Hot chocolate?
We could go hot chocolate. Okay, we can go hot chocolate.
All right.
And again, here's hot chocolate. It's outside where it's really cold. This is really hot. The heat will leave the hot chocolate to cool it down. But Miss Boyer, what do you think I could do to slow that flow of heat from leaving? How can I slow down the heat so it stays warmer longer? I can add a lid to it.
Yeah. Because that would act as an insulator.
That's right. Awesome.
Okay.
That would be an insulator. So instead of the heat leaving so fast, it would still leave a little bit.
Right.
But you'd have the little bit of convection flowing in here and in here, slowing down the flow of heat from leaving. It'll still escape, but it'll be much slower. So this cools down slower, and that's insulation. Okay?
Got it.
All right. So let's look over here. Let's look at this first.
Okay.
And then we'll get into this. Miss Camilleri and Mr. DeBack are going to do this. That's going to be a treat. Okay, here we go.
Okay.
Let's hit radiation, conduction, convection real quick. I've got a pot of water. Yes, that's a pot, and there's 3 spoons in it. We'll get into that in a second. Down here is the fire, okay? There's fire. The glow of the fire. Fire, yes, is radiation. Come on in. Is radiation. That's the glow of the fire. Now, that fire is now touching a metal pot. And when it touches that metal pot, you've got to understand metals have a low specific heat. They love to heat up fast and cool down fast. So when that pot starts to get hot, you start to see this happen. Here, I'll get down to this. Watch this. Real fast, real fast, real fast, real fast. He's traveling through the metal real fast because it's a good conductor. Whoops. So the metal pot gets hot really fast
Yeah.
because it's traveling through a solid material. It's touching the grate of the stove and the fire. But what else is going to start to get hot? The water. And you're going to notice inside the water, heat's going to start to travel. And it's going to have, watch this, it's going to go up, the heat's going to go up and down. Up and down.
It's kind of like a convection current.
This is a convection current, absolutely.
All right.
Where the water down here gets heated up and the molecules have more kinetic energy component, it rises. And then the cooler water sinks. Hot rises, cool sinks.
Right.
Wait a second, it's all because of density. When the molecules thermally expand, increase their volume, they rise to the top because they become less dense. When they cool, the particles become more dense and they condense together and they sink. So it's cooler fluid sinking, hot to the top. Cooler fluid sinking, hot to the top. Cooler fluid sinking, hot to the top. That's convection current. So the water eventually starts to get warm. Okay? Now, 3 spoons are in here. First one we're going to look at is plastic. The plastic spoons, here's the heat energy. It doesn't travel too far up the spoon. Because plastic is an insulator, it does not conduct heat and electricity. It's kind of stuck at the bottom. It's not getting hot up here. It's not getting hot, it's stuck. Here we go. Wood, same thing. Not a good conductor of heat or electricity. Heat gets stored down here, but it takes forever to move up because it's an insulator. It slows the flow of heat. It doesn't allow heat to travel through it. So you put the metal spoon there, here's the hand. Ah!
Yeah.
Burn my hand! Because why? Watch what happens here. Where the heat gets kind of slow and doesn't travel fast, this goes, watch this. Did I just sound like a dog? Okay. That was awful. This is where the heat goes up really fast because metal has properties where it can allow heat to travel through very quickly through the metallic bonding. And we're not there yet, that's in the spring. But anyway, heat and electricity can travel through it very well. It has low
Good
specific
conductor of
It's
heat.
a good conductor. That's why a lot of your metal spoons have a plastic handle, which takes forever to heat up. Okay?
Right.
All right? So metal is a good conductor. So again, convection is transfer of heat through a fluid. A fluid is liquid or gas. Conduction through solid material, and radiation is through visible light, electromagnetic waves. The light of the flame is our source of radiation here. And last but not least, Camilleri, Mr. DeBack, anybody else? Need you. Here's the heat flow. Heat enters. Right away, kinetic and thermal energy go up. But then, what happens to temperature? Sometimes it goes up fast, sometimes it goes up slow. Hello? So, you coming? All right, I'm finishing up here. Come on in. Hey, I'm just finishing this up. So if it takes forever to heat up, it's got a high specific heat. If it heats up right away, low specific heat. And the same thing down here. Heat leaves right away, kinetic and thermal drop. But if it takes forever to cool down, then its temperature will eventually go down. Whereas here, heat leaves right away. Kinetic and thermal energy go down right away. It cools down quick. You have the temperature drop. Now, we have a demo for this. But real quick, this and this. This one right here. You okay, Miss Boyd, with this camera thing?
Yeah, I'm trying.
And this go together. Because both of these have a low specific heat. These two go together because they have a high specific heat. All this is the same except right here. These two go together because they heat up right away and cool down right away. Because they don't take much heat to change. Low specific heat. These take forever to heat up and cool down. Higher specific heat. And I think we're going to do a nice
That's what
demo
we're
on that
gonna
now.
see.
Okay. You
All
got,
right.
So what do you want us to do?
All right, I want you to stand over here next to the chairs. You come over here, Miss Barcy.
Is this safe?
Well, I don't know. How's this table? Is it?
That's the wobbly table, but
It's
I'll
the
stand on the table. Oh, yeah. Oh, wait a minute. No, I ain't standing on that. I'll stand
that
on this. This one's good.
Are you sure?
Oh, yeah.
Or you could go that up there.
You want me to fall again?
Nah.
You love
All
see,
right.
you're
Look.
worried about hold on, what
Yeah.
am I doing?
Just do right there. That's good. That's good. Stand right there.
Here.
Yeah. Now,
Okay, watch these cards.
All right.
now we're not being like too picky here. We're just using whole numbers
All right, I'm
that
trying
I
to.
made up.
All right, I'm trying to focus in on the card
Oh,
here.
sorry. There we go.
All right, wait.
Specific heat of 3. Just
Okay.
to show that that's a low specific heat.
So I've got
So-
a specific heat of 3.
You have a low specific heat.
What do I have? What do I have?
Oh gosh.
Are you
oh
going to be
gosh.
one?
Sure.
Okay.
Sure.
All right. Do what? Hold on. Come on in.
It should be a compound. Two or more atoms chemically bond together.
There you go.
Oh
Look.
geez, dropped it.
All right. So your specific heat of 11. High specific heat. We're just making up numbers here.
Okay, sure.
So wait a minute. He's a substance and I'm a substance?
Yes.
You're here to be the referee?
You're the sun. Here you go. You can be the sun.
Without you, we wouldn't be able to function.
What is it?
All right. The J is a joule. So we're going to give a joule to each substance
Right now?
right now. Okay. There
Ooh, my
you
kinetic
go.
energy and thermal energy going on. Ooh, I have more energy.
Okay. Now,
Woo!
did your temperature go up?
I have a specific heat of 3.
And you got 1 joule.
I got 1 joule. I'm
Yeah.
getting there though, man.
Think
Not yet.
Did you go up? I don't know. Okay. Go ahead, another joule.
You don't have to do this, Mr. Beck. I understand.
All right, up 2. No, keep going. Another one. Uh-oh. Your temperature went up. Ah, very good. Mr. Back, did your temperature go up? No, you've got to get to 11.
I'm heating up fast.
Yeah.
Low specific heat.
All right, keep going, son. No, he. There you go, give him another one, so
Yeah, I
it's
lost
even,
myself.
because you're,
Here.
that's
4. I
5.
got 5. I'm ready to
5.
go up another degree.
There you go, give him. Oh, another degree.
Oh boy.
All right, I gotta stop. Okay,
Yeah.
assume I'm shaking. I'm getting tired. Okay, but
Yeah.
assume I'm going crazy and expanding.
So, you had a low specific heat. You
Yes.
got the same amount of energy as Mr. Back
So wait,
with a
so-
high specific heat.
so
His
it-
temperature didn't change.
So I only took 6 joules. The heat entered me. 6 joules. My kinetic thermal energy went up right away. I went up 2 degrees right away. He got the same amount of heat. His kinetic thermal energy went up, but his temperature did not go up because he's got a higher specific heat. How many joules does he need to up his temperature?
He needs 11 total.
See, that'll
Just
take
sitting
forever.
there, just
He's
sitting there.
just sitting there.
Just sitting there.
temperature's not going up. So he'll take forever to heat up. And guess what? What if he had all those 11 joule thingies? He'd have to give all those back too.
Yeah, so we can start giving them back. Now, Miss Santel, you're an ice cube.
Warm and cool, that's what it means. Here we go.
There you go. Up, energy's
I got
leaving.
5.
Energy's
Oh,
leaving.
get that. 4. I'm almost there.
All right.
Right away I
Oh,
dropped.
there you go. Temperature went down.
Ooh.
Mr. DeBack's just hanging out over
I
here.
never went up and I'm not going down.
No.
I'm still
Even
status
though
quo.
energy's added, energy's being taken away, didn't change your temperature. All right.
So I heated up quick and cooled down quick.
That's right.
And he took forever to heat up and cool down.
Yep.
So just like up here, I guess I would have been like this right here. Heat up fast,
Yes.
cool down fast,
Right.
right?
Like the sand on the beach.
Yeah, they call me Sam, they call him the ocean. There you go. Look here, this is Mr. DeBack. You know, our kinetic thermal energy went up, but he took forever to heat up and cool down because he had a higher specific heat.
And from there, then that's going to influence convection currents. We saw that land breeze, sea breeze.
Well, we're in
And you
that
have
this
lots
week.
of air molecules moving around.
Can I say one thing?
Yeah.
That was outstanding. That was great.
Is that fun with the cards?
Can I
That was
can I say something else?
Wait, did you find that on Pinterest?
I did not find it.
What is that? I don't want to know. All right, now look here, now wait a minute. I just advertised the insulator drive.
Oh, very good.
But I can honestly tell you, I feel lots of convection current. I'm like getting very hot right now.
Yeah.
Because I got 1, 2,
Oh.
3, 4 thick layers. No, 3 thick layers and a t-shirt on. 4 layers. So heat, should be leaving my body. But the thing is, I've got all these insulators on because my body temperature is 98, right?
Right.
It's a cooler environment, 60, 70, whatever. I've got all these insulators on me. So the heat's still leaving, but it's getting trapped inside these insulators. So you have a lot of convection currents developing within this air, you know, right between, you know, the layers of clothing. So the heat doesn't leave me fast, so I stay warmer longer. So please, do we have anything else to add? Because I want to talk about the insulator drive.
No, I think we're good.
Insulate the community.
All right,
Bring
bye,
in those
thank
insulators
you.
with high specific heat. I'm nice and warm right now. Can we please, once again, we hit the canned food drive. There are 2,100 cans. Let's go for insulators. Join that Friends and Community Club. Help them out. They do a lot of good. Okay? Help out your community. Spread our love of learning. My gosh, we give the community a lot of energy with food, chemical energy. Now let's spread our learning with heat. Let's allow heat to stay with people. Let's warm them up. All right? Let's spread our passion for learning. There we go. Anything else, Miss Boyer?
No, I think we're good.
All right, we are done. Study, you got a lot going on.
All right.
We're
Winter
good.
Wonderland week.
Winter Wonderland week coming up. Here we go.